3, 2, 1, 0. Commit liftoff. We have liftoff. 5, 4, 3, 2.
Roger, down here. That's the only way to fly. God bless all of you on the good earth. That's one small step for man, one giant leap for mankind.
Apollo came to an end on December 19, 1972. The age of lunar exploration was over. Now, more than 30 years later, the challenge of preserving its legacy has just begun. Hi, I'm Steve Thomas, here at the Kennedy Space Center, where the shuttle Discovery is being readied for its next voyage to the International Space Station. The shuttle was designed as a kind of SUV, a space utility vehicle, the idea being that it would help make space travel routine. And aside from the disasters of Challenger and Columbia, we barely pay attention to what's happening in space these days. But there was a time some 4 decades ago when the whole world was watching.
Engines on. 5, 4, 3, 2. All engines running. Launch commit. Liftoff. We have liftoff 49 minutes past the hour.
The mighty Saturn V rocket launched all the Apollo missions to the moon. Over the course of the program, NASA put 12 men on the surface of the moon, the first time human beings had ever set foot on another celestial body. It was an achievement rivaling the Manhattan Project, and possibly even the pyramids of Egypt in its technical scope and complexity. But now all that hardware, the spacesuits, the test vehicles, even the rockets themselves, is falling apart. And a critical task today is to preserve these pieces of history.
I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth.
Apollo represents the first time in human history in which humanity has moved off of this planet and has journeyed to another one and set foot on it. And that's enormously significant. And to explore that, to understand it more fully, to understand our place in the cosmos is what Apollo was all about.
Through the 1960s, enormous resources were poured into the Apollo program, more than $130 billion in today's dollars. 500,000 people from 20,000 companies built the launch facilities, rockets, and spacecraft that would take men to the moon.
It had just never been done before. They were going 25,000 miles an hour to a world 250,000 miles away with no way of coming back if only one component failed.
Apollo was the program that put men on the moon. What got them there was the largest rocket ever built, the Saturn V. Captain Eugene Cernan is one of America's most celebrated astronauts. During the Gemini 9 mission, he became the third man to walk in space. He was the lunar module pilot for Apollo 10, and as commander of Apollo 17, he was the last man to walk on the moon.
I've ridden the sister ships to this rocket twice, and I look at this, and we're only a quarter of the way up to the top, and I'm amazed. I mean, how did we develop it and do it? And this took us to the moon. And this particular vehicle right here, this particular Saturn V was ready to go to the moon on a flight following mine.
All engines running.
The Saturn took everything that we had learned in all those previous programs and wrapped it into one magnificent vehicle that towered so far off the launch pad that in a foggy day down at the Cape, you couldn't even see up to the top of that guy.
The Saturn V rocket is 363 feet high, almost 60 feet taller than the Statue of Liberty. It weighs 6.5 million pounds.
It has 7.5 million pounds of thrust, which could literally lift a naval destroyer off the ground. And in fact, many people compare the launch of a Saturn V the equivalent to launching a naval destroyer straight up.
This is something to realize that I was on the top of this thing. And I keep saying that when we got into the top of this Saturn V, we were halfway to the moon. I felt like we were on our way.
This engineering marvel was made up of more than 3 million parts, designed and built exclusively for each mission. Stages 1, 2, and 3 contained the engines and fuel that powered liftoff and the initial ascent. The spacecraft lunar adapter, or SLA, held the lunar module that took 2 of the 3 crew members to the moon's surface. The service module powered the command module on its journey to the moon and back to Earth. The command module is where the astronauts worked, slept, and steered the spacecraft. And the launch escape system was a small rocket that could propel the astronauts 1.5 miles away in case of an emergency in the first moments of flight.
Looks good here, flight. Good agreement.
This Saturn V rocket at Johnson Space Center in Houston was built in the late 1960s for missions following Apollo 17. But the entire Apollo program came to a halt after that last successful lunar landing, so it never flew.
When the program was canceled, it went into storage for a few years, and in 1977, they decided this would be an appropriate place to display it. And it basically sat outdoors from 1977 until 2005, braving the elements and not doing very well at it.
While 2 other Saturn Vs exist, this is the only one built to actually launch an Apollo mission. The Saturn V was built to fly for only a matter of minutes, just long enough to push the Apollo spacecraft into orbit. We're extremely lucky that this significant piece of Apollo history is still around. The rocket's now being preserved by the Smithsonian's National Air and Space Museum, with grants from NASA and Save America's Treasures, a public-private sponsorship, and with matching funds. The contractor is Conservation Solutions Incorporated.
Basically, our efforts now are to halt the deterioration that's happened over the years. We're not here to restore it. To restore it would probably cost more than the original vehicle. But our intent is to historically preserve it so people, for me, particularly kids, can come and see what a moon rocket was.
The preservation project began in 2000. Once it's completed by the end of 2005, at a cost of $5 million, the Saturn V will remain at Johnson Space Center on permanent exhibit. For many of those on the project, it's been a labor of love.
It literally was in my backyard as I was growing up. This kind of feels like my baby. I can't wait to see it when I come on site. I can't just come on site and not come out and look at the rocket.
The first step was to evaluate the rocket's condition. It was a lot worse than anyone had anticipated.
It sat outdoors, had years of mildew, dirt. We literally had trees growing out of the rocket. They would take root in the foam and in the crevices. It was its own ecosystem in many ways.
Standing inside the rear of Stage 2, next to its 5 rocket motors, engineer Tim McCullough describes the extent of the deterioration.
Inside of this rocket was corrosion beyond what we had expected. The corrosion that we could see wasn't necessarily visible from the outside. We knew there were problems, but having climbed in here, we're seeing that the problems are far more extensive than what we had originally imagined. And you can look down in here, and this is the skin of the rocket, and you can see what's left of it. Nothing. If you can see from underneath, you can see daylight. There's nothing left. All this whole area that would normally take a load can't take it. We've got a main beam down there that literally doesn't exist. I was working down in there the other day and put my foot against the beam, and it just completely collapsed on me. And we're finding problems like this, throughout the vehicle.
The rocket was designed to remain vertical, not lay on its side, and that has weakened it at several critical junctures.
Some of the structures, for instance, that held up the very heavy rocket engines, especially on the second stage, had deteriorated to the point that at least one of the engines had shifted and had begun to fall.
There was no time to waste. In early 2005, the launch escape system and the command module were separated and brought to a nearby warehouse. A giant climate-controlled shed was then constructed to protect the rest of the spacecraft from the elements. The team's next task was to assess the service module, But inspecting the interior required that they lower this 24-foot-long, 5.5-ton piece of space hardware to ground level. And that was not going to be easy.
There's hundreds of bolts and screws that hold the two pieces together, so we had to actually go in and grind off the heads of some of those bolts. So it's also going to make it tricky when we go to separate the two sections. We have to pull it straight out and then sort of lift it up.
The other challenge was performing this extremely difficult maneuver in the new building itself.
The building was designed basically to house the rocket. It wasn't necessarily designed to start lifting pieces of the rocket off and moving them around inside the building. So we have very limited ceiling height. Although it's 53 feet high, we have a crane that has rigging attached to it that is then picking something up that's 13 feet in diameter.
The service module landed on Earth without incident, and after hundreds of bolts were carefully removed, the interior was seen for the first time in almost 3 decades.
Well, as my great-grandfather would say, it doesn't look good.
We have a web that runs from fore to aft. It divides the service module into 6 segments. It runs the entire length of the service module. It's corroded away, so the pieces of metal that you see where they're ragged edges, that's corrosion.
A game plan was formulated for the service module. Extract the accumulated debris, eliminate the corrosion with high-pressure water jets, patch holes with epoxy and wire mesh, and restore the surface. The preservation team encounters new challenges with the command module and launch escape system. This was rocket science. The Saturn V was designed, tested, and built by a team led by German scientist Wernher von Braun. During World War II, von Braun spearheaded for the Nazi war machine the development of the V-2 rocket, a guided missile used mainly against English and Belgian targets. At war's end, he entered the U.S. through Operation Paperclip, the code name for a plan devised by American intelligence and military services to covertly secure key German scientists with expertise in chemical and nuclear weapons and rocketry. The Saturn V was perhaps their greatest triumph.
This was designed for one purpose and one purpose only: put men on top and go to the moon. That was it. Everyone we sent came back. Everybody we sent to the moon came home.
Each of the 13 Saturn V rockets NASA launched from 1967 and 1973 was built to fly only once. The only part returning safely to Earth in one piece was the command module.
99, proceeded, 3, 2, 1, ignition. Right away, Houston. That's your grid.
But the technology used to design and fly these rockets was, compared to today's space vehicles, primitive.
We had people in the 60s without the computers and the software that we design stuff with today, doing all the calculations by hand and not having the computer-aided design to actually help manufacture things. They did this stuff by hand. And to me, it's a marvel.
Apollo 17 launched at night, first and only flight that launched at night. And you get in that spacecraft and strap in, and the last guy says Godspeed and shakes your hand and closes a hatch, and then there you are. I'm walking into a spacecraft that's going to take me somewhere on a voyage out there into the universe. And you can feel the rumble when, they get down to 10, 9, 8, 7.
6, 5, 4, 3, 2, we have ignition.
The whole Saturn V is alive. I mean, it's almost trembling.
The S-1C first stage ignited seconds before actual liftoff, forcing 15 tons of kerosene and liquid oxygen per second into its 5 engines, generating more power than 85 Hoover dams.
The first stage burned for 2.5 minutes, and in that 2.5 minutes, it pushed this rocket from 0 to about 6,000 miles an hour.
After rising to an altitude of 38 miles, the work of the first stage was done, and it was jettisoned.
Good ignition on the second stage.
The spacecraft jettisoned the S-2 second stage once it reached an altitude of 115 miles.
Go for orbit. Go for orbit.
Those are kind words, Robert. We're go for orbit here.
The S-4B third stage, consisting of a single engine, burned for just under 3 minutes, enough to push the spacecraft into orbital velocity of 17,500 miles per hour. It orbited Earth until a go, no-go decision was made by Mission Control in Houston. With a thumbs up, the Stage 3 engine accelerated the spacecraft to 24,500 miles per hour to reach escape velocity, the speed needed to overcome Earth's gravity and send the craft to the moon. At a warehouse near the Johnson Space Center, the Saturn V preservation team is now tackling the command module. 11 feet long, 13 feet in diameter, and weighing 6.5 tons, it was built to withstand temperatures up to 5,000 degrees on re-entry. The plan for this command module is not to restore it to look like new, but to clean it and arrest any further decay. This is an impressive sight, Patty.
Welcome to Command Module 115A, Steve.
This was built to fly.
Yes, it was. It was assembled at North American Rockwell in California in the early 70s.
It appears to be painted white.
Well, it wouldn't have originally been painted white. This is the original phenolic resin surface, but they painted it white over the years to match the rest of the rocket.
Just to make it look pretty?
Yeah, just to make it look pretty.
So you're stripping it?
Yes, that's our goal, is to remove the multiple paint layers down to the original surface.
What are you using?
We actually found that using a commercial solvent-based paint stripper worked just fine to remove the paint and not disturb the phenolic resin below.
So this is what the original module looked like, right?
Yes. It looked like this, and then prior to being prepared for flight, a mylar was applied to it.
To reflect the sun. That's why when you see the pictures of them, it's all shiny.
Yes.
And that, I guess, burned off when it re-entered. The heat flashed that mylar off. Well, as I look around, I see this incredible detail work. Every copper wire is in a bundle, and it's tied by hand and labeled. It's a hand-built spacecraft. Can we go inside?
Sure.
The door itself is a piece of art.
Yes, it is, and it's heavy, too.
How much does it weigh?
About 200 pounds. We actually didn't know what the condition of the command module was on site because we couldn't get this door open.
Why did you think it wouldn't be in good condition?
Well, we saw a lot of corrosion, and we removed that pane of glass and found that there wasn't that much more damage.
An Apollo command module at launch was packed with technology and equipment. While a typical automobile contains around 3,000 parts, the Apollo command module had more than 2 million, squeezed into a space about the size of a compact car. And snaking through the craft was 15 miles of wire, enough for 48 small homes. When the Apollo program ended in 1973, all the wires on this command module had been installed, but not the controls and equipment. So this was a production capsule, but they hadn't installed the rest of the gear, and that's why we're seeing all the wires and pipes and so on?
This actually was installed. This was the environmental control system for the inside the capsule.
And then behind you is the food locker?
Food locker, where they would have stored all of their freeze-dried foods. Those holes up there would have held the navigational telescope, and this would have been the navigational panel. And down here, where you have all these covered wire bundles, this would have been the navigational computer.
That machine had less computing power than one of today's low-end cell phones. The control panel next to it, which was just as archaic, nevertheless featured 24 instruments, 40 indicators, 71 lights, and 566 switches.
The goal of the conservation of the command module is to preserve it in a moment in time in the early 1970s in its production period.
And when you're all done?
When we're all done, we'll put a cover over the lunar module hatch, and we'll close the main hatch, and then we'll have it brought back to Johnson Space Center, where it'll be put on display with the rest of the rocket.
The one part of the Saturn V that luckily never had to be used is the launch escape system.
The LES is a good example of basically of the challenges of an entire rocket because of the fact that we have dissimilar metals, we have dissimilar materials, and a lot of the same conditions of peeling paint and cracking surfaces exist here that exist everywhere.
So what material is this?
This is Inconel, which is a form of stainless steel.
And then here, where we see this massive cracking?
Cork that's attached to a ferrous-based steel. You could see the problems that we're facing, multiple layers of different types of paint that are causing cracks in the surface that moisture is getting in, gets underneath, and causes it to blister and pull away from the surface.
And back here, these cones?
Plastic or early forms of resin material that have been coated, some more iron in contact with stainless steel. All of this mixed with the polluted environment in Houston creates basically a big galvanic cell, causing these materials to deteriorate at different rates.
During the launch phase, the Boost Protect cover kept searing temperatures as high as 1,200 degrees from the command module. And this looks like a real mess. Explain what is happening here.
This is a cork material that's been applied over a synthetic plastic, essentially. We have the same sort of phenomena, again, multiple layers of paint on a very soft surface. We'll be filling the cracks with a lightweight filler material. It gets applied to the surface, it gets sanded smooth so that we can eliminate all of these cracks so that they don't telegraph or come through the coating system. Once that's done and it's sanded smooth, we're going to apply a acrylic emulsion to the surface that's basically an adhesive.
This is just commercially available at any home center. You can buy this to patch up your dining room wall.
Exactly. This is a material that is flexible. It stays flexible when it goes on the surface and acts like an adhesive that this non-woven geotextile material gets applied to the surface.
So you wet it down and then you put this stuff on.
Exactly, and then we come back and we apply a layer over the top of it.
And this is what it looks like when it's done?
This is actually a sample that's been painted, and this is essentially what the finished product is going to look like. On hard metal surfaces, we're going to utilize water jets, and we've done testing in the range of 10 to 50,000 psi for the removal of these coating systems, and really 20,000 psi is most effective for removing the coating without disturbing the underlying metal.
Then you prime it and paint it just as you would any surface?
It's an acrylic-based system that we're applying, and then an aesthetic top coat that's going on top of that.
How many gallons altogether?
Well, I talked to the paint manufacturer, and I don't know the exact gallonage, but he said it was not going to show up in a pickup truck. It was more or less basically 2 18-wheelers.
And you'll be brushing it on yourself as your project this summer, right?
Yeah, with your help.
Apollo Flight Director Gene Kranz takes us inside mission control and shows us how 40-year-old technology worked like a dream.
Apollo 13. Odyssey, Houston, we show you on the mains. It really looks great.
Gene Kranz was an Air Force pilot testing high-performance jet fighter aircraft before joining NASA in 1960 and ultimately being named flight director for the Gemini and Apollo space programs. Kranz was lionized in the film Apollo 13 and was awarded the Presidential Medal of Freedom for his extraordinary efforts in leading the team that saved the crew.
I think the LEM spacecraft is fully capable of getting the crew back.
At Johnson Space Center in Houston, Kranz took us into one of the most significant sites in the American space program.
This is mission control. It was really amazing. You could walk into this room and the front end would be bathed in this surreal blue because these were the group displays that the controllers used to provide situational awareness for the mission. We were operating down at the Cape and they made the decision to move mission control and the manned spaceflight operations to the Houston area.
Starting in 1965 with Gemini 4 and continuing for 30 years, this was command central for the remaining Gemini flights, Apollo, Skylab, and 70 shuttle missions. But through the 1970s and 80s, the equipment aged rapidly, and NASA found it unproductive and costly to maintain. In 1995, it replaced Mission Control with a new facility in the same building for the space station and shuttle missions. The old Mission Control has been preserved as it was during the Apollo program. The room has been designated a National Historic Landmark and remains a shining example of an historic site successfully preserved.
Now, we used the same basic concept that we had developed in Project Mercury. We had what we call a trajectory control team. In Mission Control today, we call it the trench. And they had probably the toughest decision time frame of any of the controllers in the mission. Virtually every one of the decisions they made was in the order of seconds. The second row in Mission Control is the systems role. We broke the spacecraft into two components, one associated with guidance, navigation, control, and propulsion, and the other one with all those things you need to stay alive in space. Power, oxygen, pressure, heat, you know, those kinds of things.
The average age of the flight controllers was just 26. Krantz, in his 30s during the Apollo program, was the old man at Mission Control.
This is my console up here. I was the flight director, and very simply, I had the job to take any actions needed for crew safety and mission success. During the course of the mission, there was no higher authority.
One of the most challenging moments Krantz ever faced as flight director occurred during Apollo 11's final descent to the lunar surface, when Neil Armstrong and Buzz Aldrin were about to become the first human beings to land on the moon.
Okay, all flight controllers, go for landing. Retro, go. Fido, go. Guidance, go. Control, go. Telcom, go. GNC, go. Ecom, go. Surgeon, go. Capcom, we're go for landing.
Eagle, Houston, you're a go for landing, over.
During the way down, my trajectory controller guidance officer indicated before we'd even started down that we were halfway to our abort limit. We had a series of computer program alarms, and as we got down close to the surface of the moon, we don't have a gas gauge, a fuel gauge, that basically will read all the way down to zero. Once we get to the curved portion of the lunar module fuel tank, we have what we call low level.
Low level? Low level.
And we would normally land with about 2 minutes fuel remaining. Now, we see that we're going past that 2-minute period. We're now past 60 seconds.
60 seconds.
60 seconds.
I have a controller calling me and he says 30 seconds.
30 seconds.
30 seconds. Forward, head more forward, drift into the right level.
And we're still several feet up in the air.
So what's going through
and the
your
crews, well, I'm really at the process now where we're faced with a very, very difficult and risky land abort decision. And the only calls I'm getting are fuel remaining. And as soon as we hit zero, it is up to the crew to either land or abort at that instant because theoretically we're out of fuel. I had a hold of these handles in the console. And basically, as we were getting now into this final countdown, I had a hold of the one with my left hand. I was writing with my right. I have a foot key I use down on the floor to communicate back to my controllers. I have all of these voice loops coming in off the panel, or I'm listening to the air-to-ground loop. I'm listening to my own controllers in there. And this whole thing converges on this decision we're about to make. And then we realize
Tranquility Base here. The Eagle has landed.
that the crew has landed on the surface, and they're going through shutdown. At the time that we landed, we had about 17 seconds of fuel remaining. And it was probably the closest we have ever come to making that extremely difficult land abort decision.
Tranquility, we copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
This room, Mission Control, is on the National Register of Historic Places. Why is it important for us to preserve the machines, the remnants of the Apollo program?
Mission Control is a unique place. It represents the earthbound control facility that took Americans into outer space. So when you say this is one of the National Historic Landmarks, this is the window to space where we developed the technologies. We believed in this dream that we had been given by John F. Kennedy. And we made it happen.
We investigate spacesuit technology, and Buzz Aldrin shows us how his Apollo 11 equipment worked on the moon. The Saturn V rocket and mission control at Johnson Space Center aren't the only artifacts from the Apollo space program being preserved for future generations. The spacesuits worn by the astronauts of Mercury, Gemini, and Apollo are today carefully safeguarded at the Smithsonian National Air and Space Museum by curator Mandy Young.
I consider the suits to be miniature spacecraft, the smallest spacecraft of all. They're historically magic, really. They're the only ones that did what they did. There was never a failure with a spacesuit. They kept those guys alive there and back and on the moon. And then the guys who thought them up, who made them work. That was an incredible set of brains that did all of that.
Spacesuits have come a long way since the days of the old sci-fi films. In the 1950s and 60s, NASA put the development of spacesuits on the fast track, though some testing procedures at times seemed like Little League tryouts. The spacesuit ultimately developed for the Apollo astronauts was called the A7L. It contained 22 layers of materials, including Teflon, Mylar, and nylon, providing protection from biological hazards, thermal radiation, fire, and abrasion. On Earth, it weighed almost 50 pounds. On the Moon, with its 1/6 gravitational pull, only 8 pounds. Mandy Young's efforts to preserve NASA spacesuits take place at the museum's Paul Garber facility just outside of Washington, D.C. She took me into the humidity and temperature-controlled environmental unit, where several dozen spacesuits are preserved.
When Kennedy said, let's go to the moon, spacesuit development began in earnest, and 2 lines of development were actually worked on. One was soft and one was hard, and this is an example of a hard suit.
I can touch it?
Yes, you may. The suit is hard all over with all the movement built into the joint system itself.
Well, the engineering is magnificent. Look at this.
This is a later model of the same suit.
What were the advantages of a hard suit?
Well, when you pressurize a spacesuit, it has a habit of blowing up like a balloon.
So if it's hard, then you can pressurize it and
it stays the same shape. It retains its shape, and because all the motion is built into the joints, as it is in the human body. Then this is a lovely suit. This is a very early developmental Apollo suit.
Here, the articulated joints are soft.
Yes, this is called convolute, and it was put together by a man who saw a tomato worm and realized that that motion could be translated into a rubber and nylon joint.
So the joints themselves are flexible but compressible, so you can fold the suit up.
And they only expand in one direction.
And how about the cables?
Well, this cable's kind of cute. There are two in the front and 2 at the back, and they're to hold the helmet down, because when you pressurize a suit, the helmet would come up and you wouldn't be able to see out, and so these were to hold that down. Steve, these are my babies. These are the prize of the collection. They're the lunar suits, the ones that went to the moon. This one's Alan Shepard's. He wore it on Apollo 14. And over here, what we have is what I consider to be the prize of the collection. This is Jack Schmidt's Apollo 17 suit. He and Gene Cernan were the last 2 men on the moon.
So the dust that we see here is a piece of the moon.
Absolutely. You're
I am touching the moon.
Yes. And this is Jack Schmidt's boot.
So it is woven stainless material on the cuff.
and the silicone base.
Well, it's amazing to think that the footprints made by this boot are still there on the moon.
Yes, it is. This spacesuit was worn by Mike Collins. He was the command module pilot on the Apollo 11 mission, and it was on display downtown in the museum inside the command module.
At the Smithsonian?
At the Smithsonian for the past 29 years.
Wow. So how did it fare over 29 years on display?
Well, why don't, if you would help me turn it over, I'll show you on the inside there. This is showing plain textile deterioration. But if I pull this liner open, you can see all that black stuff on the inside here. And
so that's the natural rubber and the neoprene
absolutely.
rubber reacting?
Yes, and it's also coming from the zipper here. As you can see, it's got two zippers.
Mm-hmm.
And one of the zippers is full of rubber, and this is actually what held the pressure.
Yeah.
And because it's a brass zipper, and brass contains copper and rubber don't interact at all this rubber has deteriorated and is breaking off, and that's part of it.
So as a preservationist, what can you do to minimize the deterioration that's caused by these dissimilar materials?
Well, you can keep them clean. You can keep them in an even environment, and hope that in the future, like all good archaeologists do, that somebody will come along there will be technological advances, and that above all that you do no harm.
You know, it's amazing to think that these suits flew in space and walked on the moon in some cases, and I can only imagine what it was like to wear one.
Well, there's someone here who has actually been there and done that.
Before he was chosen by NASA in 1963 as an astronaut, Buzz Aldrin was a fighter pilot during the Korean War and then earned his doctorate from MIT in Manned Space Rendezvous. On July 20th, 1969, Neil Armstrong and Buzz Aldrin walked on the moon. 35 years ago, a little bit longer than that, you stood on the moon wearing this spacesuit, which you haven't seen in how long?
It's been a couple of years and at a distance and through glass.
So here it is.
What a
You got your white gloves on.
What a privilege to get close to it again. I can remember taking things out of the pocket.
Yeah, like what?
I remember putting a little packet that was to be left on the surface of the moon. We left a silicon disc that had the names of the leaders of 75 countries around the world in a statement that they prepared. And then I think there was a patch of representing the Apollo 1 crew, Gus Grissom, Ed White, Roger Chaffee, who died in the Apollo fire. The plaque that we left, "We came in peace for all mankind."
Dear men from the planet Earth, first set foot upon the moon, July 1969, AD.
Now, this is the item that I think reflects very nicely. And when Neil took that great picture of me on the moon,
right.
his image and all the rest of the background showed up as a reflection in that image. On either side, they're sort of blinders.
What were those for?
Well, in case you're working continuously in a certain position and the intense glare of the sun is bothering you, and there's no atmosphere to filter the sun and its intense glare, and that's why we have this gold visor.
I've always wondered what it would be like to stand on the moon and look back at the Earth.
If you're right in the center of the moon, the Earth is going to be straight up, and it's going to generally stay there. Now, with the suit on the way it is, you can't really see. Is that right? You got to sort of lean back to see home, see the Earth, where everyone except 3 human beings exist. And the 2 of us are down there, further away than any human being's ever been. And I think of all the sense of feelings that we had, it was that this is historic. This is a once-in-a-lifetime opportunity. And we've been given that fortunate opportunity to do that. We better make sure we do things right.
Restoration on a lunar rover prototype kicks into high gear. This is the Odyssey, the actual command module from the Apollo 13 mission. It's on display at the Kansas Cosmosphere and Space Center. The Cosmosphere houses one of the largest collections of space artifacts in the world. At its warehouse, Vice President Jim Remar gave us a behind-the-scenes look.
This is the Cosmosphere's north building, our backstage closet, if you will, of our space artifacts.
Stacked to the rafters.
Stacked to the rafters, absolutely.
What's this?
This is Mariner 5. This was an unmanned planetary explorer that went to Venus. This is an engineering mock-up that was done by JPL.
Jet Propulsion Laboratory
That's
in
correct.
Pasadena, California.
And behind it, we have an X-15. This is an engineering mock-up of the X-15 that was done by North American Aviation, and they use this for wind tunnel testing.
So that's an actual test piece?
That is correct.
What's this?
This is the nose to a JBL loon. This was developed during World War II by the Germans and then adapted by the Americans after the war.
Mercury?
This is a Mercury capsule, a mock-up. It gives you a really good idea of the size and shape of the Mercury.
Yeah, a trash can.
Trash can, exactly. And these are two sets of Titan engines, the XLR J87s. So the type of engine that was used on the first stage of the Titan rocket.
This whole unit sat at the bottom of that first stage?
That is correct. And then this is the same thing, just standing up vertically. And then behind us is an Atlas engine. This is the type of engine that powered John Glenn into space, America's first astronaut into orbit.
So these are all working engines, or were at one time?
That's correct. And then we have a Saturn V instrument unit. This is the brains behind the Saturn V. This sat on top of the third stage of the Saturn V rocket.
So these three sections would have been assembled in a ring.
That's correct.
And would sit up on top of the third stage,
Correct.
and they guided the whole ascent of the rocket
That's right.
into space. So what are you working on now?
This one's a monster.
The lunar rover was a small dune buggy that was driven on the lunar surface for 3 Apollo missions, beginning with Apollo 15. It increased the distance Apollo astronauts could travel to make geological observations, perform scientific experiments, and collect rock and soil samples. The vehicle, powered by an electric motor and batteries, had no gears or transmission. It was designed for low speed and high torque, topping out at about 8 miles per hour. The 10-foot-long rover traveled to the moon in the lunar module, packed into a 4 cubic foot space, and was unfolded by the astronauts once they landed. On Earth, it weighed 460 pounds. On the moon, only 76 pounds, light enough for 2 astronauts to lift. Coming up with the right lunar rover took years of R&D. In the early 60s, NASA commissioned prototypes from several companies, some with rather distinctive designs. One prototype was this one from the Bendix Corporation that Cosmosphere is now restoring.
Well, here in the main workshop, we're working on what's called the Bendix Mobility Test Article, which is a mouthful.
It is a mouthful, and this monster was supposed to go to the moon?
It was. NASA was developing a couple types of vehicles. One that would do short exploration of the lunar surface and eventually became the lunar rover, developed by Boeing. And then they had GM, Bendix, and Brown Engineering develop mobile laboratories.
So they envisioned big vehicles ranging across the moon?
Absolutely, for prolonged exploration of the surface. And so they had to invent different types of technology, such as the wheels here. This is made out of aluminum and stainless steel, and you can see the springs, which give it its shock or absorption, and then it also had to have traction and be lightweight.
Where did you find this thing?
Well, we rescued this in the weeds outside of Marshall Space Flight Center in Huntsville, Alabama, where it had been rotting for over 20 years. And we're going to restore it for the National Air and Space Museum.
How do you restore something that's a one-of-a-kind?
Well, let's ask Rod Gibbons, our restoration manager.
First thing we're going to do is we're going to dismantle the wheels, and we'll probably use a soda blasting process, which is less aggressive on the metal.
Than sandblasting?
Right.
So you take the paint off?
Take the paint off. It doesn't attack any of the metal. And then one of the guys is already welding up some of the tears in it.
What about all the wiring? You must have miles of wiring on this thing.
It's pretty well corroded, and we're going to have to go in and clean it all. And as you can see, it's all brittle, and we'll replace a lot of the tubing.
How did they steer the thing?
What we have is 2 joysticks, one front to back, and then one left to right. And there again, that's what Jack is working on. Both of them are broken off, so these will have to be fabricated.
So the whole control panel up there needs to be figured out and then rebuilt?
Totally restored, yes.
You're going to repaint the frame?
We're going to sandblast the frame and have it powder coated.
And when you're done, it'll look just like it came out of the Bendix shop.
Brand new.
When do I get a ride, Jim?
Well, in about 4 to 6 months, we'll have you back and we'll take you for a ride.
If we believe it's our destiny as human beings to explore new worlds, then we can look back with pride and wonder at a time when ordinary people were called to an extraordinary task. They didn't know it couldn't be done, so they just went out and did it. Today, preserving the stories and the artifacts of the Apollo program is our task. For the History Channel, I'm Steve Thomas, and thanks for watching.